The following programme contains details of real murder investigations to demonstrate chemistry and biochemistry techniques used by forensic science. A young woman is missing. Fears grow she has been murdered.
On entering the property, I'm apprehensive. I don't know necessarily what I'm going to find.
A suspect's house is scoured from bottom to top in search of evidence. A young boy is attacked by a gang on his way home from school. He's cut by a broken bottle and bleeds to death. The case remains unresolved for years.
This is a diagram of the right training shoe.
A new team of forensic scientists are brought in to re-examine the evidence. Murder investigations depend on forensic science. Forensic science depends on chemistry and biochemistry to uncover the facts. Forensic scientists have numerous techniques up their sleeves to identify blood, clothing fibres, body fluids, and DNA. This machine finds needles in haystacks. It can locate one molecule among millions and turn an alibi into a lie, or confirm the cover-up of a murder.
I received a call from the police to ask me to attend with them to a property. This was the property of the suspect in a murder investigation, this being the murder of Chantelle Taylor, who had been missing for over a year. I was asked specifically to concentrate on the upstairs in the property, given the information that the suspect had given. I went to examine the main bedroom for any blood staining. Underneath the carpet there was a large area of blood staining, about 1/2 metre by 1 metre in size. We would still use the screening techniques because it's further confirmation that yes, that red-brown staining is blood. The chemical screening test that we use for blood is called Kastle-Meyer.
In forensic science, Kastle-Meyer is used daily, on a daily basis, both in the lab and at the crime scene. There's Kastle-Meyer itself, which is actually something called phenolphthalein, and another chemical is hydrogen peroxide. And hydrogen peroxide is the same stuff you use to bleach your hair.
We take a small piece of filter paper and take a very small sample of a blood stain that we can see, or an area that we want to test, maybe where we can't see any blood but there may be some there.
To demonstrate Kastle-Meyer, we placed a trace amount of blood on a bedsheet.
What we then do is apply 2 chemicals to the filter paper where we've used to sample an area.
The Kastle-Meyer test reacts with the haemoglobin in blood. And it's actually something within the haemoglobin that's called peroxidase activity. So peroxidase is an enzyme, so it's the enzyme within haemoglobin. What will happen is the peroxidase activity within haemoglobin and blood kickstarts or catalyses the reaction or decomposition, if you like, of hydrogen peroxide. So hydrogen peroxide will react with this blood. The hydrogen peroxide will become oxygen. And then that oxygen is the key to the entire reaction. And the oxygen will then be passed to this phenolphthalein, which will make it change colour.
So what we're actually looking for is a change in colour, which is basically a pink colour.
The Kastle-Meyer test is a very sensitive test. They do say that it should be able to detect 1 drop of blood in an entire bucket of water.
The suspect had indicated that the bathroom was very important in relation to what had happened.
The suspect actually admitted to waking up one morning to find Chantelle Taylor dead and dismembered in his bathroom. He claimed to have no memory of killing her.
From a visual inspection, I couldn't find any blood staining. So I then went on to carry out chemical screening. We also have another tool in our chemistry box. It's a technique using a chemical called luminol. Now this is highly sensitive.
Luminol is just a chemical called luminol and hydrogen peroxide. So the same way that Castlemayer has hydrogen peroxide in it, phenolphthalein, luminol is luminol and hydrogen peroxide. Luminol reacts in a really similar way to Castlemayer. The difference really is that instead of a colour change that you see in the reaction, you actually get a release of light. So these two chemicals react together and it produces a blue glow, so light's released, and it's a process called chemiluminescence.
This chemical reaction can only be seen in the dark. So all sources of light have to be sealed off.
Ordinarily, when two chemicals react together, they produce heat, but in this specific reaction, they produce light.
Even though we used these highly sensitive tests, we didn't find any blood.
The next area of the house to be inspected would lead to forensic science history.
The suspect said that he had put Chantelle in the loft. My role as a forensic scientist was to examine that loft. I would expect to have found blood in the loft. I didn't find any blood in the loft. But what was very apparent and what I did find was pupal cases and dead flies. This indicated that there was a food source present in the loft. We were interested in whether this food source possibly was Chantelle Taylor. From the information from the police, I understand that Chantelle Taylor took drugs. Could we find support that maybe the maggots had, on passing through the food source, fed on a food source that contained drugs?
I'm head of a group called Ecology, which includes entomology, which is related to bugs and maggots and things like that. And she called me and said, gee, we're at a scene, we found these casings. Could you do anything in toxicology? And I said, well, we've never done this before, and in 26 years I'd never heard of it. And I said, but I always like giving anything a go.
Giving it a go meant firing up the GCMS to test the fly pupae casings.
Gas chromatography, mass spectrometry, or GCMS, it's combining gas chromatography with identification using the mass spectrometer. So the gas chromatography is for a separation technique on its own. However, the identification comes from the mass spectrometer. So by combining the two together, you have a really useful instrument in forensics, in chemistry, in science in general.
So we stuck these, there were 4 or 5 of these little casings, and into methanol, which is a solvent, and put it in the fridge for a week.
Methanol was used to dissolve any chemicals out of the fly casings.
Then we used that little vial of methanol and we analyzed the methanol.
When you place your sample in the autosampler, it injects your sample into the gas chromatograph.
The injection process is automated to ensure uniformity. The injected liquid is vaporized in an oven and converted to a gas. The gas is then transported through a very fine tubular coil called a column. The journey through this fine tube becomes a molecular race in which an element's boiling point is key.
Depending on what's present in the sample, its boiling points will be quite critical.
Different boiling points affect travel time through the coil. Each element shows up as a peak when it exits.
Those different peaks have a certain retention time associated with them, and that's the time at which they were injected to the time at which they've come out of the column. And it's unique to particular compounds, so it'll give you a certain amount of information about what might be present if you compared the retention times to known retention times. After your sample has been separated into its individual components, then we need to identify those particular components using the mass spectrometer. Basically, your sample is bombarded with a beam of electrons, which causes your molecules to fragment with a particular fragmentation pattern, which is unique, like a fingerprint for that particular molecule. And on that basis, you can identify what's present.
And we found morphine, which is a drug in itself, but is a metabolite of heroin. And so it was really the first time in the world anyone had ever analyzed the casings and found drugs in them. It helped a lot in the case that we found that there were those metabolites there. The victim's body was never found, so really all they had is these remnants of particles in the attic.
Sometimes investigations and courts fail to resolve a major case, and forensic scientists take a second look.
Damilola Taylor was 10 when he was murdered in Peckham. He was on his way home from the library after school and was stabbed. It seems that he was attacked by a gang of youths. He was stabbed in the leg with a piece of broken bottle, and unfortunately he sustained a fatal injury. He bled to death in the stairwell of a block of flats.
There were two highly publicised trials in the Damilola Taylor case, which had not yet led to any convictions.
The police approached our laboratory and they wanted us to re-examine the case. In the end, I had 20 lever arch files like this, which contained DNA profiling results and my statements. We were asked to examine a lot of items of clothing and footwear from the suspects in the case. We looked at a black sweatshirt from another suspect and we found a blood stain on the cuff of that black sweatshirt. In this case, we used a test called luminol. The yellow crayon shows where we'd found blood originally. There's some luminescence within that area.
The use of luminol had identified bloodstains previously overlooked.
This is a diagram of the right training shoe. We looked at a pair of shoes from one of the suspects and we found a blood stain on one of his training shoes. Now these two blood stains were then put in for DNA profiling tests. So that's one on the trainer and one from the sweatshirt.
DNA profiling has had a revolutionary impact on forensic science since the 1980s.
With a blood stain, we need to get the DNA out of the cells, and the DNA is contained within the white blood cells. There's no DNA in red blood cells. We extract the DNA by breaking open the white blood cells, so the DNA is now in a solution. We want to multiply the amount of DNA there so that we've got enough to analyse it. In our bodies, when we cut ourselves, cells regenerate, and that process involves DNA amplification or replication. So new DNA is being made in our bodies. Polymerase is the enzyme which causes DNA to replicate. So it effectively moves along the DNA molecule and it causes the two strands of DNA to separate, and then it brings in the building blocks of a new DNA strand, and the polymerase enzyme puts together those building blocks and builds it alongside the existing DNA strand. And in our DNA profiling process, we take those same chemicals that replicate DNA and we use them effectively in a test tube to amplify DNA.
The amplified DNA from small blood spots on the suspect's clothing was then tested.
They both gave profiles matching that of Damilola Taylor.
A third trial in the case of Damilola Taylor resulted in convictions.